Hi, today I will be deriving a forward differencing scheme to calculate the time-varying temperature profile along a bar. So to give you guys a better visual of this, let's draw the bar. And we'll draw some increments about it. Right, and so then we have increments along this bar, and we want to find the temperature at each of these increments. So we have some delta x here. And each increment can be labeled as j. So our x value will equal our j times our delta x. So if we're at position 4 and our delta x is 1 meter, we'll be at 4 meters along this bar. So that being said, we want to find the temperature profile at any given position in this bar. So to do that, we'll first start with our equation, which is the derivative of temperature with respect to time is equal to our thermal diffusivity times the second derivative of temperature with respect to position of x. Clear. All right, so what we're going to do, first assumption is that there's no heat generation. There would be a different term in here if there was heat generation, but because there is none, it's equal to 0 and cancels out within the equation. So first what we have here is we'll take the derivative of this, and we're going to use finite differencing approximation to solve this and to get that differencing scheme we're talking about. So first we'll do our temperature, and this is with respect to time. So we'll have n plus 1 at some, so this is the temperature at some position j at some time n plus 1. So then this will be minus the temperature at n at some position j. This whole thing is then divided by your change in time. And this will equal alpha, your thermal diffusivity, times. And then basically what we'll do is split this up to make it easier to comprehend. So then we'll have our derivative x times, and then this is the derivative of temperature with respect to x. So basically what we did here is just split that up. And so to find this, what we'll first do, circle that, throw that over here. We'll have the temperature at time n, but at the position to the right, minus the temperature at the same time n, but at the specified position. So this would be, if this was our specified j, it would be the temperature here at this node minus this one. And then all of that is divided by your change in x. Then you subtract that from your temperature at some position n or at some time n at some position j minus the temperature at a time n at some position to the left j minus 1. And all of that is delta, all divided by your change in position. And so then what you do is then take the second derivative for that. So then this whole thing will be divided by your delta x. And so if you plug this in, the alpha, and then this, we can simplify and then have a formula that can calculate the temperature profile along this bar here that we specified. So we can have our T n plus 1 j equal to alpha, and then we move the delta t over, delta t, and these have denominators that are the same, and so then this will just become delta x squared, and we're going to pull that out of this term here. Delta x squared, so then times our temperature at time n some position to the right, minus 2, because there's 2 of them, times the 2 times the temperature at some position J at some time n. And then minus minus would be a positive, so then plus the temperature at some time n, but to the left of the specified node. And so basically what this is saying is the temperature at some position J at some later time n plus 1 is equal to this here. So what it needs to end up finding that using our finite differencing is the temperature at the node to the right of the specified one, the temperature at the current node that we're looking at, and then the node to the left of it. So you need the temperature at n, here, here, and here, to find the temperature at, say this is J, this would be J minus 1, J plus 1. So we need the temperature at some time n here, the temperature here, and the temperature here to find the temperature at a later time n plus 1 at this specified position. And so what we're going to do is then use this and put it into Python to calculate the varying temperature profile along this bar. So now that we've completed number 2, which was to derive an explicit forward differencing scheme for calculating the time varying temperature profile, we'll now move on to number 3, where we're implementing that and then showing how that through that implementation that there will be stable and unstable results for our specific values of the discretization. Alright, and so then I have this that I'm going to use as a reference to type in our values. And so what we have here, we have our libraries. This is just to calculate things numerically, and then this here I didn't feel like memorizing, so I just copied and pasted it over. This is how we're going to use our subplots to graph it and look at our values and calculations visually. And so to get started, we can just plug in our knowns. So we'll have our delta x. Actually, let's start with our thermal diffusivity, which was 1. So alpha equals 1. And then we have our number of spatial increments across the bar. And so this will be 50. I believe it was 50. Yes, 50 meters, and then each step size will be 1. So our dx will be 1 meter. So we can type that in. Dx equals 1 meter. And then our nt, so our number of time increments, can be anything. So we can just put that as 2,000. And then our dt, we will start it as 0. Let's do 0.1. All right. And so then we can also do our R value, which helped us simplify our equation earlier, which we see right here. And that is alpha times our delta t divided by our delta x squared. So let's get back and type that in. So that is our alpha times our t. Space this out so it's easier to tell where things are being done. And then our dx squared. So that's our R value. And so then now what we're going to need to do is we're trying to find that profile. So we need an array to do that. So we're going to do our temperature array, but we don't have anything for that yet. So that'll be, we use np.full. So what this does is it'll take the shape of the array, which will be how many increments. So we want to find the temperature at each increment. So it's going to be nx is the shape of the array. And then we can put in our value for the temperature along that array. So this will, every value in the array will be this value here. We'll do 20. But first we can show you that it will, our first index will have temperature equal 50, and then the temperature at the last index will be equal to 80. Alright, and so then what we're going to need to do is iteratively calculate our values for temperature using our equation that we solved for right here. So we'll use a for loop to do that. So we'll do for I in range, and then we're going to do our first value to nt. So that's how many times it's going to calculate. And so then we'll put in our equation. And so what we're going to do is slice this array up specifically to account for the fact that we're using temperatures at previous positions and later positions at the same time. So this will be temperature. And so we actually already know our outside temperatures. So T0 is equal to 50. So that's our first temperature along the bar. So that's the leftmost position on the bar, and then our rightmost, the outside, will be 80 degrees. And so then what we're going to want to do is find the inside temperatures. So that'll be the second value, and then right before the last value. And that is equal to, and so let's reference this again. So it's going to be equal to the same thing, but then plus all of this because we don't know what they are yet. So one, and then is R. Yep. R times, and then it'd be, I believe it was the, so this will be the temperature at the same time, but one position to the right. So in order to do that, we will have 2 to the end. And then that will be minus 2 times, and then this is just TJN, which is the temperature at the specified position at the same time. So then T, what we said for that was just the 1 to -1. So that's our inner temperatures. And then plus the temperature. These are the temperatures to the right, or to the left. Alright, and so then when we have that, so when we do this, we want to just plot. We don't want to plot this many because we have NT, we have 2,000. We don't want to plot that many. So in order to make a graph that's visually pleasing and makes sense, we want to plot for every multiple of 100. So if so we're going to use the modulus thing for that. So percent 100 equals 0. Space that out. We're going to add our plot. So actually, in order to do that, we're also going to need values for x. So what we're going to do here is make an array for x. So that's going to be np.arange 0 to x. And then this is going to be multiplied by our delta x. And that's what's going to be calculated on the x-axis of our graph. So we have that. Let's actually first plot our initial, what that'll look like. So that should just show us 50 on the left side, 80 on the right side, and the rest of the temperatures being 20. So then we'll do fig equals make. Actually, let me run this so when I'm typing this in, I don't make an error. Make sure that goes before I keep going. Alright, so we'll do fig equals make subplots, yep. And then we'll do, it's only going to need one row and then one column because we're only using one subplot.
a scatter plot for this. So if we go add or scatter, and then x will equal, like I said earlier, x is going to equal this x array right here. So we actually haven't run that yet. I'm going to comment this all out so we can do that. All right. Okay. And y is going to equal that temperature array, so we're going to see how that temperature varies as we change in position along the bar. And the name, we'll name this one initial, just so we can see it visually. Alright, so we have that. Alright, that should be good. Yeah, so as you can see here, this is our initial without any of the temperatures being changed through this equation. So when we made that array, we had 20 for every single value except for the first and last. So that's our first, it's 50, which we made here, and then our last being 80 up here. And that's along the increment specified with the x array. And so then we're going to iteratively calculate the rest of the temperatures in the bar. Alright. So then, yeah, so since we now are going to plot for every 100, we'll do fig dot add scatter. X still equals that x array. Y still equals the temperature array. This time we'll do modes equals lines. I think it's mode, rather, not modes. And then the name of it, we'll make that equal to, yeah, we'll do that. So then it's going to be equal to the iteration value that it's plotting. So then we can tell that it's correct. Alright. And then once we have that, we can then show it. Alright, so we have that, we have our x array. Alright, this should work. Alright, so we're having a problem with our formula here, so let me make sure that's correct before we continue on. Let's see, so operands cannot be broadcast together with shapes. Alright, so what I'm going to do now is actually stop the recording right now and take a look and make sure that this is correct, and I'll come back and explain the fixes I made for this code right here. Alright, so after looking at the code for a little bit, I saw that the error was right here. I had a +2 rather than -2, so I was just not taking correct values when calculating. And so, exit this out so you can see it when I run it. So now I'll run it and it should show, yeah, so this is every 100 increments, and it still shows our initial that we have here, and then it shows how the temperature changes along the bar. And so if we just change this, make it 0.5, and then run it, looks a bit different, it varies still. But now, to emphasize the instability of this, if we change this to, say, 0.55, our graph will look a bit different. And so now you can see that it shoots up to values that range from 1.5 times 10 to the 147th power, which is insanely big value, and then this is such a small value close to 0 right down here. And so this is obviously incorrect. Our formula put in was actually correct. It's just the way in which our R value calculates these. That because of R being greater than 1/2, we get a value that's unstable. So we can put that back down to 0.4 and it'll become stable again. Yeah. And so it's actually not this dt that's changing it, it's the fact that all of these within that affect r are changing it. So because we have alpha equaling 1, 1 times 0.4, 0.4 divided by 1 squared is 1. So then r in this case is just going to equal whatever dt is. So it's really r that's being affected rather than dt. So as you can see here, we'll do 0.505. Yeah. So now it's a smaller value than, I think it was to the 147th power, but now you can see it's starting to become smaller. And then we can do 0.501, might be close to stable. Yeah, so that actually is still stable. And then if we do 0.505, see if that changes anything. Still good. 0.503. Still 1 million. 0.502. Yeah, so then you can see more of the scatter plots and traces that we calculated. And this only goes up to 1,500 rather than trillions or to the 147th power. And so I will show why this is true and why this isn't actually incorrect in the next video.
Alright, so now we're going to find a solution to the heat diffusion equation. So let's write that out. Derivative of temperature with respect to time is equal to the thermal diffusivity times the second derivative of temperature with respect to position. Alright, and so what we're trying to do is find the solution, and we have to prove that this term here, which is t equals e to the ikx times e to the negative alpha k squared t, is a solution to this differential equation here. So what we're first going to do is take the first derivative of this with respect to temperature. So this term here, I'll rewrite this for more clarity, equals e to the I kx e to the negative alpha k squared t for time. All right, so our first derivative on the left-hand side of the equation is with respect to time. So we're taking the derivative of temperature with respect to time. So this is the only term that has it. So that'll be negative alpha k squared e the I kx e to the negative alpha k squared t. So this right here is the first derivative of temperature with respect to time. So then this is going to equal alpha times the second derivative of temperature with respect to position. That'll be alpha. So let's take so the only term that has x in it will be this first part here. This doesn't have anything to do with x, so it'll be treated as a constant. So what we do is then, you're going to do it twice, so you're basically going to do times I squared times k squared e to the I kx times e to the negative alpha k squared t. And so looking at this, it doesn't quite look the same. We have imaginary numbers on the right-hand side, but we don't on the left. But if we look here, this I squared will end up equaling negative 1. So then we have, pull this down, negative alpha k squared e to the I kx times e to the negative alpha k squared t equals, this becomes negative 1, so then negative alpha k squared e to the I kx times e to the negative alpha k squared t. And so because these are the same, they're equal, these are solutions to the heat diffusion equation specified earlier. And they're solutions to the no heat generation heat diffusion equation. All right, so now what we're gonna do is apply stability analysis to show why that R value within our code was unstable when it was greater than 1/2. So let's take our equation that we solved for. So we have our temperature at some later time n+1 at some position j is equal to the temperature at some position n, at some time n position j plus R times, and R being this value here, the thermal diffusivity times the change in time divided by the change in position squared. So that's R times temperature of n at j plus 1 minus 2 times the temperature at some time n at a position j plus the temperature at some time n at some previous position j minus 1, or a position to the left, I should say. And so what we're going to be doing is using the solution we found to our differential equation and plugging that in to help us with our stability analysis. So first can do is, oh, well, actually before I start that, it's important to note that x is going to be equal to our change in x times our node j. So j times delta x. And then it goes the same way for our time, so that'll be n times our delta t. So that'll end up being used when we plug this back in and start simplifying. So we can have this down. All right, and so this right here was equal to the time at position j at some time n. This is at position j plus 1. So basically what you're going to be doing is adding 1 here, because it's with respect to x, the position j. So it'll be, we're basically going to be taking out t position j n and times e to the I k x minus, and then this stays the same because we want to keep it with respect to the temperature at the specified time and position that we were talking about earlier. And plus, and so this is now at a position to the left of the specified position. So this is t, and then times e to the negative I k delta x. Oh, I didn't put delta x here. All right. And so now what we can do to help simplify this is use Euler's equation. And so to reference that, it's e to the I x is equal to cosine of x plus I times the sine of x. And so we're going to be using that to help simplify and cancel things out so it's easier to see. So then we have, bring this down. And we'll factor out the TJN. So then we have times R. And then we have e to the ik delta x. So using our Euler's equation, it'll end up equaling cosine of k delta x plus I times the sine of k delta x. And so then that got factored out, so that'll just be minus 2. And then we have this here, this e to the negative ik delta x. And this will be plus cosine of k delta x minus I times the sine of k delta x. So as we can see here, these can combine, and then these will cancel. And then we can move the temperature at some time n and some position j out. So then we'll have, move it down again, t j n plus 1 equals temperature at position j time n 1 plus r, and then we have 2 cosine k delta x minus 2. Yep, because that canceled, those combine, we still have the minus 2, and we pulled out the temperature. And so when looking at this, this can help us visualize why it's unstable. So if this term here is greater than 1, then the temperature at some later time at the same position will increase, and it will continuously increase and then end up increasing forever and equaling infinity. So that is why it's unstable. So then we can pull this out, factor the 2 out, and we have 1. So now we're no longer looking at this, we're just looking at this. So then we have 1 plus 2r is the quantity of cosine k delta x minus 1. And then this thing has to be less than 1, because if it were greater than 1, it would increase and then just continuously increase. So then you can move that. And so then once that's moved, we get 2r cosine of k delta x minus 1 is less than 0. And then as you can see here, this will end up showing us that our r has to be less than 1/2. And that's why it's unstable for any value greater. All right, so now that we've looked at the von Neumann finite differencing scheme, we're now going to derive the Crank-Nicholson finite differencing scheme for the heat diffusion equation. And so the only difference with this is the way in which the second derivative is approximated. So let's first write out our von Neumann just to look at it and compare. All right, so that was the temperature at some later time n plus 1 at some position j is equal to the temperature at some time n at some position j plus r times some temperature n, or some temperature t at some time n at the position to the right of the bar, then minus 2 times temperature at some time n at some position j plus the temperature at some time n, but to the left now, at some position to the left of j. All right, and so the only difference now is the way that we approximate this second derivative. So just to reference that and get a clear visual, the heat diffusion equation was this. The derivative of temperature with respect to time is equal to the thermal diffusivity times the second derivative of the temperature with respect to position. Right, so our R in this case was alpha times delta T times, or divided by delta X squared. So our Crank-Nicholson is going to look very similar, but with one difference. And so let's write that out. Crank-Nicholson. And so same thing, temperature at some later time n plus 1 at some position j is equal to temperature at some position j at some time n plus, so I'm going to expand our R value out here because it'll change with this approximation. That's going to be plus alpha times delta T over delta X squared. So now what we have, same thing here, but the only difference now is that we're not just referencing the 3 positions across the bar to the right and left of position J, but we're doing the same thing, but now at a later time as well, and then we're going to average the 2. And so we have the temperature. We're just going to basically copy this down, put it here. So the temperature at some position to the right at some time n minus 2 times the temperature at position J at time n plus the temperature to the left at some time n. And now we're adding that, and then we're doing the same thing. We're basically copying and pasting this, but now at the later time n plus 1, same thing as here. So it's going to be temperature at position to the right, but now at a later time n plus 1 minus 2 times the temperature at J time n plus 1 plus the temperature to the left at a time later n plus 1. And then you basically have these 2 quantities, you're adding them together and then taking the average. So then it's divided by 2. So then what we're going to do is pull out the 2, so we'll put it right in here, and then our new R value is going to be this. So now R, I'll put R here, put it in a box. R equals alpha delta T over 2 times delta X squared. So that's going to be our new R value for the Crank-Nicholson approximation. So now once we put that in, we'll get temperature at sometime n plus 1 at position J is equal to that plus R being that now, and then we're just going to write this out. All right, so now we have that, and so we've derived the Crank-Nicholson finite differencing scheme right up here. That's what this is. But now what we're going to do is show why this is better in some instances than the von Neumann. It's a little harder to calculate, but our R value is going to have no constraints, and that's what we're going to be doing right now. So what we do here is move everything with terms of n plus 1 over to the left-hand side with this temperature at a later time, n plus 1. So to do that, we then have, okay, so then we have negative R, because that gets moved over. Yep, okay, so negative R, T at some position to the right, n plus 1. And then we have minus 2 times the temperature at some position J at a later time n plus 1. And so then we get plus 1 plus 2R temperature at some position J time n plus 1. And then minus R temperature later time, but now to the left. And then this is basically, it's going to look exactly the same on the right hand side for the temperatures. It's the time n, except it's going to be 1 minus 2R. So then we have, let's see, yep, R times temperature at some position to the right at time n, plus 1 minus 2R temperature at time n, position J, plus R times temperature, position n, or time n, position J minus 1, position to the left of position J. And so then what we're going to do now is put everything in terms of the temperature at position J, whether it be n+1 on the left side or time n on the right side. So we're going to get everything with just the J. And so in order to do that, we're going to use the Euler Formula, which we saw earlier when proving why R can't be greater than 1/2 for the von Neumann stability. So it's e to the ix equals cosine of x plus I sine of x. And so we're basically going to be doing that. So we're pulling out one from here and one from there, but we're going to the left and right. So we'll see for this, we have negative R times the temperature at J, because we're pulling out the one, n+1, e to the I k delta x. Because we're only moving with respect to the position. That's why we don't reference this part right here that has, it references time. So then plus 1 plus 2r. And this one we don't change because it's already at position J. And then minus r, and then it's making it with respect to position J rather than the position to the left. And then now that's going to be e to the negative I k delta x. And then this whole thing equals, on the right hand side, we're going to do the exact same thing, just now at time n rather than n+1. So then we get r to the j, e to the I k delta x. Yeah, and then plus 1 minus 2r temperature J. So we don't need to change that one, just like this one. It's already at the position J that we wanted at. And then plus R times the temperature at J at time n times, and then we're going to the left, so it's e to the negative I k delta x. And so we're going to further continue with this problem once I get more room on my whiteboard. So I'm going to stop the video here and start later. All right, so now that I have more room on my whiteboard, I've just taken the equation I had down here and moved it up. So now what we're going to do is use our Euler formula and basically plug in and substitute in values. But before that, the only thing I'm going to do differently now is move this, like divide both sides by this quantity here. So we have temperature at J at some later time, n+1 equals the temperature at J at some time n times, then we have R e to the I k delta x plus 1 minus 2r plus R e to the negative I k delta x divided by this quantity here, negative R e to the I k delta x plus 1 minus 2r plus r, or minus r e to the negative I k delta x. All right, and so this e to the I k delta x, let me see. So what we saw earlier is that this can be modified, and we'll end up getting this. So we'll have temperature J n+1 equals temperature at J at sometime n. And then we'll get quantity 2r cosine k delta x plus 1 minus 2r over negative 2r cosine k delta x plus 1 minus 2r. All right, so now that we have this, what we're doing now is just making sure that any value for r will not cause this to exceed a value of 1. Because if it does, then you have a value greater than 1. It's going to constantly be increasing every time at any later time. So then this value here is just going to go off to infinity. So we're only looking at this now. All right, and so then we can factor things out with this, and we'll get, let's see, get 1 minus 2r let's see what that would be. Yes, I think it's 1 minus cosine k delta x over 1 plus 2r, then 1 minus cosine k delta x. Let me make sure this is right before we go forward. Okay. So then what we can see here is that this value, this 1 minus cosine k delta x, is always going to be positive because the cosine function can't exceed a value greater than 1. So then we can just call that y. So we'll have y equals 1 minus cosine k delta x. All right, so then we can move that over. We have 1 minus 2ry over 1 plus 2ry. All right, so then we have that. So let's write this here. Y will always be positive. And now that we have this, we can, these are the same term. So then it can be like, we could just call 2ry z. So we have 1 minus z over 1 plus z, z being 2ry. And so then we can see for this, that this will always produce a value less than 1. So this whole thing is this just simplified for a better visual of seeing why this thing is always going to be less than 1. So this is always going to be less than 1. Therefore, it's stable at any value of r, which is why the Crank-Nicholson finite differencing scheme is so important.
All right, so now that we've derived the Crank-Nicholson differencing scheme for the heat diffusion equation, we can now implement it into Python so we can visually see the temperature profile as a function of time. And for this, we'll be referencing these two matrices. And so what basically each one is the left one is basically solving for all these temperatures at a time n plus 1. And it has all of these, we don't know what the values are, but we have these basically coefficients in front of them. So we have 1 plus 2r, negative r, and negative r. And then the right matrix is just the right-hand side of the equation. And so this is going to be a matrix of size spatial increment minus 2 by 1. And so when I say that, I'm being general. So for this, it's a 4 by 1, meaning there's 6 total, but then you're subtracting 2 because we know the outer and inner. The right-hand temperature and the left-hand temperature of the bar, basically the outside temperatures. So we don't know the inner temperatures, and so it's going to be same logic over here. We have spatial increment minus 2 by spatial increment minus 2. So if we have 50 spatial increments, it's going to be a 48 by 48, which takes into account, same thing over here, the outermost temperatures that are known already. Okay, so now that we know that, we can move on to our code. So what we have here, we're going to use linear algebra to solve these matrices. So we need to, from scipy dot lin alg, import it's solve banded. Yeah, so we have that. So now we can run that. So now we know it's in there. And then we're basically just going to copy and paste this, our knowns, down into a different cell, this one for the Crank-Nicholson. So then we have this, but the only difference now is that our R value has changed, which we saw earlier. So it's now 2 times x. All right. And so then what we're going to do is set our temperature array again. So it'll be T, let me see how I did it up here. Yes, we're going to fill an array with certain values. So np.full, the size of it, the shape is going to be spatial increments, so nx, and then we're just going to fill it with values of 20. Alright, let's just see what that is. Let's run this, and then run this. Yeah, so we have, I think it's 50, yeah, we have 50 spatial increments, and then we're filling it with 20. So we can delete that. Alright, and then we're going to put in our known, so we know the outermost temperatures, so 0 equals, I think we said 50 for the first one. Let's do the same thing. And then, so our last value of our array will be 80. So basically our outermost temperature on the right is 80. The outermost temperature on the left would be 50. And then every other temperature within this array is going to be 20. So let's run that and show. So T, run it. Yeah. So you can see 50 on the left side, 80 on the right, everything else is 20. Alright. So then now that we have that, we can move on to our solving the matrices. So that being said, we're going to be doing this. So as you saw here, we have diagonals of all the same values. So we have negative r on this diagonal, 1 plus 2r on this one, and then negative r on the one above. So we have upper and lower diagonals. And so this solve banded that we imported is going to take however many lower and upper diagonals we have. So let's make a matrix of those diagonals. So we have, call it A. So A equals, let's allocate it first, so np.zeros. And so as you saw on this, we have 3 different diagonals, so we're going to have 3 rows, basically. So 3, well, it's got to be 3, and then it's spatial increment minus 2. Alright, so if you run that, and then we show it should be, yeah, so we have 3 different rows, all of zeros, and the size of each row, like however many zeros there are, is nx minus 2, so it's 48 in this instance. So let's get rid of that. And then what we want to do is fill in the negative r, 1 plus 2r, and r into this zeroed array of values. So first we're going to do, let's see, so we want to put in the upper diagonal, and this is going to be first value, no, or no, this is the first row, so we have 0, and then as you can see over here, it doesn't start till over here, so we're going to move accordingly, so we'll start at 1 rather than 0 and go all the way to the end, and this will equal negative r. And then, so now we're going to fill in for the second row of zeros, and that will be 1 plus 2r, so we have 1 comma, and so then for what values do we want to fill in whatever this is going to equal, and we want every single one of these, so it's going to be 1 plus 2r filling the entire row, because as you can see here, it goes all the way through. So that's going to equal 1 plus 2 times r. Okay, and then now we got to fill in that third row, which is still negative r. So this is going to be our lower diagonal. So yeah, 2, because it's the third one, and then what values do we want? So as you can see here, we have negative r, and it starts at the first one, but it stops before the last one. So go here. So that being said, it's there for the first one, but it's not there on the last one, so we'll put negative 1 there, and then equals negative r. Alright, so now that we have this, we can move on to our B array, which is the right-hand side of the equation. So we have B to capital B. B equals, and we're going to allocate this array as well. But this is only in spatial increment minus 2 by 1 array. So that being said, we only need to fill in the shape for it. So we np dot zeros, so we're allocating it. And then it's just going to be nx minus 2. Alright. So then B, what does B equal within this array? So let's actually see what that is. Yeah, so B is that 48 by 1. Alright. And so what does B equal? It's that right-hand side of the equation we saw here. So right there. We're basically going to be plugging that in. Alright, and so then we have B equals, so then it's that first term, what was that? R times the temperature at the position to the right at time n. So that will be R times the position to the right, the temperature at the position to the right at time n. So that will be position to the right. Okay. So yeah, that'll be 2 to the end because it's everything to the right of the bar. And then I think it's minus 2 times, let me check. So plus. So then plus the quantity 1 minus 2 times R times temperature, and that's it. These are all the temperatures. It'll be 1 to negative 1. And then same thing, plus R times temperature from beginning. This is the leftmost side, so this is every position to the left. And so then it'll be negative 2 on that. Alright, so then we have our B array. We need to find our inner and outermost because, as you can see here, it's referenced, it's added on again. So let's go back and we have B of 0. And what is this going to equal? It's just going to equal itself and then plus R times T at a specified position. Let me think about what position that's going to be. Right here, so T0. Okay. Look at this one time. Yeah, okay. It's B0 plus R times T0. And then you got to do it for the last value as well. So then B negative 1 equals B itself. So R times, and then add negative 1. All right. And so this is going to be very similar now that we have our array, or our diagonals and the arrays for all of this. The only thing different is that we're going to do the solve banded in between. So we can pretty much just copy this down because it's going to solve it iteratively in the same way, because we don't want it to plot every single time, because we have 2,000 time increments and that'll just be a mess to look at. So take this, okay, and let's rename it so you can call it CN. So everywhere there's a CN or a fig, we can put CN because it's CrankNicholson. CN. Alright, so that's the name of our graph. We have one row, one column. X equals that X array we still have up here. Y equaling the temperature array. And then, let's see. This is going to change because we have our solve banded now and we have different arrays. Yeah, so let's move this. So then it's going to equal solve banded. Let's do that. So how many upper and lower diagonals do we have? We have 1 and 1. So, and then it's asking for that AB, which is just our A in this instance, and then B. And that's it for that. So then what we want is to move these down because they change. So we can just Control-C, Control-V, indent these correctly. Alright. So this should work, and this will show us the temperature profile as time varies, but for the Crank-Nicholson approximation. So if we just let's make sure we've run everything. Let's run that. We don't need to worry about the von Neumann one. And then we can run this. And it should give us... Oh, I think we have to show it. Or maybe CN. Alright, so this does not look correct at the moment. So what I'm going to do is take a break here, look at the code, see if I made any errors, and then come back and explain what errors were made and correct them. Alright, so after looking at the code, I couldn't find any syntax errors, but instead I just started playing with the code, and then I remembered back to lecture about changing things to floating points. So I started doing that, and that ended up being the case here. So let's do this, we'll run it, and then we get a temperature profile. This one for the Crank-Nicholson approximation, and then in order to show the stability constraint, I made R. I manipulated values to make R greater than half, just to show that it does work for values over that. And even though it is harder to calculate the temperature at a later time, this is useful for that reason.